All right, team, today we're going to work on 3.4 properties of logarithms. So you're going to want to have your graphing calculator handy because we will be doing a lot of calculations in it just to kind of compare and see what's happening with these different properties. So be sure to go ahead and grab that. I want to start today with just a basic exponent review. So just things that we've seen before and maybe we just need a little bit of a refresher on is looking at these basic properties. So when I have the same base, and these bases are being multiplied together, what we do is we end up adding those exponents together. So for example, if you had something like x squared times x to the third power, this ultimately becomes x to the fifth power because you have 2 factors of x times 3 factors of x, and you in total would have 5 factors of x. Likewise, if we are dividing things with the same base, then we end up subtracting those exponents. So that would simplify to a raised to the m minus n power. If we have something that is being raised to a successive power, so a to the m raised to the nth power, this would be equivalent to a to the m times n power. So these are our 3 basic properties of exponents. The other thing, just to kind of remind ourselves, when we see a fractional exponent, not to be scared of them, a to the 1/2 power is completely equivalent to a to the first power, and we're taking the square root of it. Now I put a lot of extra numbers in there, so it would ultimately look like that, but we are lazy and there is a 1 right here and a 2 right here that we don't write. Similarly, a to the 1/3 power would be equivalent to the cubed root of a, and then something like a to the 2/3 power would be equivalent to the cubed root of a squared. Okay, the denominator becomes the index, so what root you are taking, and the numerator of the exponent becomes the exponent on the base. Now, looking at some properties of log. So in your calculator, go ahead and type in these 3 different log expressions. So the nice thing about your calculator is you do have an actual natural log key on there. Now, things to keep in mind, natural log of 24, you should have no issue typing in. It would look like this in your calculator screen. The natural log of 2 plus the natural log of 12, you do need to be careful. Your calculator is going to prompt you with that first open parenthesis. You do need to make sure you close that parenthesis before doing plus the natural log of 12. And then same with this third one, natural log of 4, close the parenthesis plus the natural log of 6 and close that parenthesis. Go ahead and try those 3 and see what you get. All right, all 3 of these should have yielded the exact same value. So they all should have yielded about 3.1781. Okay, that's rounded to 4 decimal places. If you didn't get that, you need to double check your parentheses on those second 2. So what that's telling us is these 3 are all equivalent to each other. So the natural log of 24 is the exact same thing as the natural log of 2 plus the natural log of 12, which is the same thing as natural log of 4 plus the natural log of 6. So the whole idea here is to kind of look at and be like, okay, so if the natural log of 24 is equal to the natural log of 12 plus the natural log of 2, well, where can I get 24 from the 12 and the 2, and where can I get 24 from the 4 and the 6? And hopefully you can see that you are actually multiplying those 2 numbers together to end up with that 24 that we have over here. So this brings us to our product property. Log base b of m times n is equivalent to log base b of m plus log base b of n. And hopefully this makes sense. When we started with that exponent review, logarithms are just exponents. So they are going to follow the same rules as exponents. So if you are adding 2 logs together, it would be equivalent to multiplying the arguments of those 2 logs together. So let's look at simplifying. So we are going to actually write this as a single log. So you might see the directions in Connect as condense. Okay, so you are writing these, you're taking these multiple log expressions and you're going to condense this down to having only 1 logarithm. So things to take note of here is these both have the exact same base of 5. So that's a good thing. That means they're the same base. And if we are adding them together, then this will be log base 5 of 4 times 3. So this will ultimately be log base 5 of 12. Now, if I could actually simplify this, if I knew whatever power 5 needed to be raised to in order to get 12, then I would go ahead and actually simplify that. Since that's something that I don't know, this is my final answer. That's written as one single logarithm. All right, so this would be a lot more fun if we were actually in a group right now. But go ahead and just think about all the different ways that you could write log of 36. All right, hopefully you had a chance to do a few. So you could get, mildly creative. Maybe log of 12 plus log of 3, because 12 times 3 is 36. What about log of 6 plus log of 6? So this one's kind of interesting because 6 times 6 is 36. And then notice you actually have two like terms. So one of something plus another one of the same something would give you 2 of the something. So this one we might actually explore a little bit later, but just another way to write it. Maybe let's get real crazy. How about log of 9 plus log of 4? I'm just looking for two numbers that multiply to 36. So I'm going to keep the same log base, and then I'm going to add those two logs together. All right, let's look at simplifying something that looks maybe a little bit uglier. Log base 1/3 definitely isn't very pleasing to the eye, but let's see what happens when we simplify. And also note these directions of simplify. This means I'm probably going to get a nice answer, like a numeric answer. So we're going to have log base 1/3, and then if I have the plus sign right here, that means I'm going to take the 27th and multiply it by the other argument in the log. So it's going to get multiplied by the 1/9. 27 times 1/9 would give me 3. So I'm left with log base 1/3 to the 3rd power. So here's where I'm asking myself if I need to simplify this. Sometimes it helps just to kind of set that equal to x so we can see what we're dealing with here. So 1/3 raised to what power is going to be equal to 3. So this 1/3 right here, I have the 3 that I need, but I need to move it from the denominator up to the numerator. So if I had 1/3 raised to the negative first power, that would be equal to 3. So that tells me that this whole thing right here would be equal to -1. All right, let's use a calculator to compare now log of 30 versus log of 300 minus log of 10. So notice this is the common log, so you have a log button on your calculator. Again, when you type in the second one, you need to do log of 300, close the parenthesis, and then minus log of 10, close that parenthesis. All right, doing that, you should have gotten the exact same answer for both of those. And I got something like 1.4771. So that's saying 10 raised to the 1.4771 power is about 30. And hopefully that makes sense because 10 to the first power is 10, 10 squared is 100. So it's going to be a little bit bigger than 1 to raise us to the 30 power. And this also illustrates our quotient property. Remember with our exponents, when we had things with the like base and we were dividing them, it showed up as subtraction. So when we introduce our quotient property here, things with like bases, we are actually going to subtract them when we are dividing the arguments of the logarithm. All right, so let's take a look at this one. Let's write this as a single logarithm. And again, you always want to simplify when possible. So looking here, we're actually going to look at this one two different ways. So let's rewrite this using the property that we just learned. So this would be log base 4. If I see this subtraction sign right here, that tells me I'm going to be dividing the arguments, and they're going to go in order. The first one is going to be the numerator. The second one is going to be the denominator. So this is going to be log base 4 of 64 divided by 16 is 4. And then when I see log base 4 of 4, 4 to what power is 4? Well, that's just going to be 1. So we were able to do that using our properties of logs. Now, let's just kind of see what happens here, because if I look at log base 4 of 64 and log base 4 of 16, I actually know what those two numbers are. For this first one, 4 to what power is 64? Well, that's really 3. And 4 to what power is 16? that's really 2. So that's completely equivalent to saying 3 minus 2. So notice we ended up with 1 working with it that way as well. All right. So for this one, think about how many ways you can write the natural log of 5. Again, I don't want you to ever freak out when you see the natural log of 5 or just the natural log in general. All it is the log base e. I actually prefer natural log in a lot of cases because it's only 2 letters to write versus the 3 letters I'd have to write with log. So natural log of maybe 25 minus natural log of 5, because 25 divided by 5 is 5. You could do natural log of 5 minus natural log of 1. Okay, anything that when I divide the two values, I end up with a 5. All right, last one that we're going to compare is, let's look at log of 3 squared versus 2 times the log of 3. For both of these, you should end up with 0.9542, about, it's approximate. And what that's telling us is we have this power property. So if we have an exponent on our log, it is completely equivalent to dropping that out front. So 2 log of 3 is equivalent to log of 3 squared. And we actually saw that when we were going through and just looking at some of the examples over here. This would be equivalent to log of 6 squared. Because isn't 6 squared is still 36, and we found out that doing log of 6 plus log of 6 is equivalent to the 2 log of 6. So here's our power property, log base b of m raised to the x power. These two are completely equivalent. Sometimes we want to be on the left side form, sometimes we want to be on the right side form. We just want to know that these two sides are completely equivalent to each other. This is probably one of my favorite properties of logs. So let's take a look at one. Looking at this, again, we're going to write this as a single logarithm. There's a lot going on here. So if we just kind of start here, I might go ahead and start with this 3. And I can move that and raise that to the 3rd power. So log base 2 of 2 to the 3rd power plus log base 2 of 4. And let's see what happens here. 2 to the 3rd I could simplify. I know what that number is. And now I have the same base, and I'm actually adding these two logarithms together. So that means I can go ahead and multiply their arguments together. So this is log base 2 of 32, and then always check to see if we can simplify this. 2 to what power is 32? Well, that's going to be 5. And if you maybe kind of noticed just looking at this in the beginning, you have log base 2 of 2 right here, so we have that property where the base and the argument are the exact same thing. So that's really equal to 1. So you could think about that as 3 times 1 plus, and then over here, log base 2 of 4. 2 to what power is 4? Well, 2 to the 2nd power is 4. So 3 times 1 is 3, and 3 plus 2 is 5. So there's just another way to think about this one because it was really nice numeric values. And the whole idea here is that the two ways to think about it should match because we're using all of the same equivalent properties. All right, let's write this guy as a single logarithm. Looks a little bit funky. I see some things. I have a fraction in here at the 1/3, but I do notice that I have that 3 out front. So I am going to go ahead and just automatically move that up as an exponent. So that's log base 9 of 3 to the 3rd power. And then probably in that step, I would have just simplified that and written that as log base 9 of 27. So let's see what we have here. Looks like I'm adding these two together. So using my product property, I'm going to go ahead and take 1/3 times 27, which gives me 9. So I'm left with log base 9 of 9. 9 to what power is 9? Well, 1. And let's simplify something like this. This one looks pretty terrible. So what you can do is this 7 plus x, notice that whole thing is the exponent. I would go ahead and drop that out front. Now, when you drop that out front, since that entire thing was the exponent, you do need to make sure that quantity stays contained in the parentheses. So this is the quantity of 7 plus x times log base 3 of 3. which this actually cleans up quite pretty. Because log base 3 of 3, you have the same base as the argument. So this is really the quantity of 7 plus x times 1. So this just cleans up to 7 plus x. All right, let's do one more condensing here, writing this as a single logarithm. This one has a lot of stuff going on. The first thing I'm just checking is that all of these are written with the same base. They usually will be. You could certainly play some games having some different bases, but for our purposes, we'll have the same base here. And I just see a lot that's going on. I see I have a subtraction sign. So that tells me that this whole piece right here is going to be in the denominator after I clean it up. I have the 4 right here, so that tells me both of the items inside of these parentheses will be raised to the 4th power. And then inside the parentheses here, I also see an addition sign. So those two would be combined with multiplication. So just like with order of operations, I'm going to start with the innermost portion here and see if I can get some cleanup work done. So just looking on the inside piece, log base 5 of r plus 2 log base 5 of t. What I can do is I see I have the 2 here, so I can go ahead and move that up as an exponent on the t. So that's log base 5 of r plus log base 5 of t squared, and then I have the addition sign. So that tells me that I can multiply the 2 arguments together. So this would be log base 5 of rt squared. So that just cleans up that inner piece. So I'm going to kind of rewrite what else I have. So I still have 4 times that entire thing. So with that 4 right there, we want to go ahead and bring this up as an exponent because it's going to apply to everything inside of those parentheses. So this will be log base 5 of rt squared, all raised to the 4th power. Now remember that our product property when we are working with, our power property when we are working with exponents, everybody inside is getting raised to the 4th power. So that's going to be r to the 4th, t to the 8th. So this is looking, I guess, a little bit better. I don't know, maybe not much. But now the last part is we have the subtraction sign right here. So I'm going to have to kind of squeeze it in off to the side because I can't extend my page on this. So we're going to have log base 5 of y and since the y is coming first, that's going to be in my numerator. And then if I'm subtracting this, everything is going into my denominator. So r to the 4th, t to the 8th is what goes into the denominator. So that would be my final cleaned up, simplified version of the log. All right, the last thing that I want to talk about here is the change of base formula. So this is kind of cool. Now, some of the newer graphing calculators let you just type in whatever. You can fill in the blank with the bases. But we do have this change of base formula if you are working with an older model calculator or if you see something like this in the directions. So log base b of x is equivalent to log base a of x divided by log base a of b. So what that means is whatever that base is, notice that's the same base in the numerator and the denominator, so you get to pick the base. So you're going to pick either just log base 10, so the common log. Oops, sorry, that's a b on bottom. Or you're going to pick the natural log. It doesn't matter which one you pick, both will yield the exact same result because they're the exact same base in the numerator and the denominator. My dad, when he went to school back in the day, they just had books of logarithms where they would have to look up in tables whatever the base was and then whatever the argument was. Way before graphing calculators or any kind of, readily available calculator was available. So this is kind of a really nice formula that whatever calculator you have, as long as you have either a log base 10 or a natural log key on it, you can evaluate any logarithm. So let's just try one. So let's just say, for example, let's evaluate. I guess I really should say approximate because it's probably not going to be a pretty answer. Let's approximate log base 4 of 153. Now I could certainly kind of figure this out, at least have an ish idea. 4 to what power is going to get me close to 153? Well, it's probably going to be between 3 and 4. would be my guess, because 4 to the third power is going to be 64, and 4 to the fourth power is going to be way bigger than 153. So it's going to be kind of somewhere in there. But what this allows me to do is I can either take log of the argument, so log of 153 divided by log of the base value, so log 153 divided by log of 4, or I can do the exact same thing but just with natural log. I tend to gravitate towards natural log because honestly I'm lazy. It's only 2 letters to write for natural log versus the 3 letters to write for log. So go ahead, try typing that in your calculator. Again, you need to be really, really careful. So whichever one you type in, you need to make sure you close that parenthesis, and then you can hit your divided by, and then you're going to have log of 4. So go ahead, try typing this in. Nothing hurts more than having a right calculation, but just an incorrect user error with using the calculator. So when I type this in, I get approximately 3.6287.